All right, good morning. Just, let's give it a little bit of time for other people to join. All right, hey Ben, thanks for joining.
Hello, hello.
Yeah, I think all right, I can't hear you, I think.
Can you hear me now?
So yeah, let's get started. I mean, get only Eric on the call, but I mean, this presentation is recorded, so we'll post it on the CNCF TAG-Runtime Slack channel. So it's should be pretty helpful for some of the folks, they want to watch it later.
Sounds good. Okay.
So yeah, take it away.
All right. Hi, everybody.
Oh,
I'm
we
Ben
can't
Wilson.
hear you. Can you or is it my? Oh,
I
I think
can hear you.
yeah.
I can hear you fine.
Okay.
Okay, cool. Okay, cool. It was just me. Sorry.
No worries. So, hey, everybody. I'm Ben Wilson. I'm a principal RSA at Databricks. So, sort of a field consulting person that helps a number of different companies do ML, do ETL, leverage Apache Spark for a bunch of different use cases, everything from really small startups to Fortune 10 companies that use our platform. And one of the things that I help really people focus on is ML ops, how to basically take an idea that they have for data science use cases with ML and make it production ready. And that's a very broad term. And I know a lot of people look for the easy button for that. Like hopefully a framework is going to solve all their problems. It's never that simple. So one of the things that we've built at Databricks is Mflo and have open sourced it to the community. And it's a broad and very flexible MLOps framework for managing not just experimentation tracking, but also the entire ML lifecycle. There's a couple of things that still need to be built into the platform to support more general use cases. It's things that we are working on that I actually can't talk about, but they will be coming soon from Databricks. But for the core critical things that people struggle with. Mflo has really helped a lot of companies wrangle the cats as part of their ML development process, from experimentation to production release. So what I'd like to do today is walk through an example of something that a lot of companies struggle with, because not due to its complexity, but more to the fact that there's a lot of moving pieces when you're talking about production maintenance of an ML solution, with regards to how do I counteract drift, how do I respond to that, and how do I automate away a lot of the incredibly painful events surrounding manually retraining models. So the demo that I'm going to be walking through shows a very simple use case of an open source data set. We'll be leveraging Mflo to do experiment tracking. And we'll be looking at all the metrics that are collected. We'll be doing looking through an automated hyperparameter tuning using Optuna on Spark, and then looking through how do we register that model so that it can be evaluated, and then automating away the human in the loop requirements of that by doing comparison of a retraining event to prior existing art of that model, and then autonomously upgrading the production release of that so that any serving system would be able to just use that new version once it's been vetted. And we'll walk through all of that and show some examples of what it looks like when your retraining is actually better than the previous one, and also what it would look like if a passive retraining isn't better than the current running one, and how that would be reflected. So I'm going to start sharing and we'll get through this demo.
That's good. Thank you.
If I can find my window. Okay, that should be the right one. There's a green highlight to it. Okay, so to begin with, Mflo, this is the main website and landing page for the open source release of Mflo. It is fully featured, and the open source version is written in Python. You can check out how the code works. You can even contribute to it if you'd like. You can fork the repo, play around with it, and it is hosted on PyPI, so you can just do a pip install of Mflo, specify a particular version, and you'll be able to get it installed on your system. It can run pretty much anywhere, and the tracking server, you can specify whatever sort of RDBMS backing you would want. So if you want to use MySQL, MariaDB, MS SQL, provided it's an OLTP database, it'll support the tracking components of that. For artifact hosting of stuff like your model artifacts, any sort of tags that are associated with that, links will be provided in the tracking server that is on the database to any sort of object store that you'd like. So, or even on-prem if you so choose. So we'll kind of see how that looks in the demo. But what we'll be looking at in this demo is the custom Databricks version of this. So we don't have the open source version of Mflo. We kind of have Mflo on steroids at Databricks. So there's a lot of custom proprietary stuff and integrations with our platform that make it pretty easy to use and eliminates a lot of the boilerplate code you would have to use in order to use the open source version of it. But we'll see kind of, what all that looks like and how the visualizations tie into the workspace platform of Databricks. So here's the demo. And to begin with, the first thing that we're going to be doing is we need to actually leverage Mflo for what it's really good for on the tracking server, which is tuning models at that level of the package. So there's a number of different ways to do that. I'd never recommend grid search. It's kind of terrible when you're doing brute force searching through stuff like that. Random search is better, but I prefer using stuff that uses a tree of parson estimators. So either HyperOpt or Optuna. Optuna has a more refined and elegant implementation of TPE than the original implementation of HyperOpt. So first thing that I'm doing here is I'm just going to install it to my runtime environment. And this is the Databricks UI. I'm currently attached to a cluster right now. We're not going to be using this cluster for any processing on the worker nodes because we're using a very simple model on very small data. We're going to be doing all of our execution on the driver. So all of this code will look kind of how you would do it on any cloud-based VM or even on your laptop. But I'm just using Databricks because I work there, and this is a nice runtime environment to execute all this. But we're going to get that Altoona installed. It'll go through just a regular pip install. And then we're going to be doing our imports. So even though we are on Spark, we are using sklearn. So there are some operations with PySpark that are going to be used in this, but that's just for the data ingestion and a couple of things that we're doing with simulating ETL operations. Not so much feature engineering stuff, but just, cleaning up the data a little bit. And other than that, we're really just going to be using Mflo. So for the key critical parts of Mflo to just get started, the only two that we need for this sklearn flavor is to just import Mflo and Mflo sklearn. And this will allow us to specify the type of the artifact that we're generating. Since we're using sklearn, we need to have that reference. And we are going to be using the client in order to access tracking events that we've been writing to it. And that's going to allow us to do the passive retraining aspect of this to compare what exists before versus what we're trying to do right now in our passive retraining event. And then signature inference. Signature allows us to embed in the actual artifact what is our actual schema. And that helps if we're going to be taking this model and sending it off to create a REST API. If we wanted to containerize this artifact and we want that REST API to interface with this model artifact to say, I'm passing in this JSON request, I'm expecting these fields to be present. This will ensure that that mapping is done correctly, so we don't get strange, difficult to diagnose bugs happening later on. So now that we have our imports done, this next part is just acquiring data. This isn't something that you would do in the real world like this, but we're acquiring an open source data set and we're adding a couple of columns using some PySpark functionality. So this data set is about the Portuguese national forest and its history over the last, I think it's like 20 years of data or something, of forest fires that have broken out in that. It's a very common data set. A lot of people use it. You could just get it from the UCI ML repository. So all we're doing here is using the driver to get that data set over to our VM. Then we're writing it to our file system in order to be able to do some stuff with PySpark on top of it. And the first thing we're going to do is we're going to be adding an additional field to that data set. So I thought it would be fun to calculate the heat index. So here's the equation for that, just done as a UDF on top of that. So, and then the Spark application here, we're just adding these columns. So we're doing some date time manipulation here, extracting out, the days. We're doing some casting from the actual string values, which these aren't standard date time formats. It's not something that any system would be able to process. So we're just basically doing string indexing here on an ordinal condition. And then we're actually adding that heat index column here. Next thing we're going to be doing is creating a database for this data to live, and then creating a table for it if it doesn't exist. So we're going to be writing it out to Delta. This is and similarly open source data storage paradigm that Databricks has built and given to the world for free. Delta allows us to use object store as if it's an OLAP database in the cloud. It's blazingly fast and it's optimized for ML use cases. So it really works if you have repeated reads from your source data set while doing algorithm training. We're going to register the data, and this is just making sure that we're getting it logged into Delta correctly. And the last little bit of this from Delta, we're going to be doing all of this training and passive retraining using pandas. So all of this is going to, all the data that would exist on executors or workers on a Spark cluster, we're going to be pushing that back to the driver. So it's just going to be single node operation that pretty much all data scientists are familiar with. The reason we're doing this is we're not using an actual distributed algorithm here. The data is way too small to use like a Spark ML implementation. So scikit-learn is the way to go with this. Here's some just boilerplate cleanup code stuff, just so that we can reference things in the Databricks workspace and allow us to pass parameters to when we execute this, instead of having to write a bunch of script that's really annoying to maintain.
So you were not using a distributed algorithm. You would actually, well, you are not using a distributed algorithm, but if you were, then you would actually do it across multiple nodes instead of just.
Yeah, there's a couple of cases where you would use Spark in ML for if you have a large scale problem and it's sort of traditional ML supervised or unsupervised learning, provided the algorithms can be distributable. A lot of stuff on Spark ML can support that. So logistic regression, linear regression, survival, AF survival regression, random forest, decision trees, all that stuff. Those standard algorithms are all part of Spark ML. And they lend towards extremely large data sets when you're going to be training on. The other way to leverage Apache Spark, which is what most of our customers who are doing ML at scale do, they might not have a large training data set, but they want to get their training evolutions to work much faster. So when you're doing hyperparameter tuning, your search space might be thousands of iterations in order to get a really well-tuned model. If you're doing that on a single node VM, that's serial generally. You can parallelize it to a certain degree, but you're limited by the threads on that single VM. So what Spark allows you to do is take that even smallish data set that can reside on a single VM, and we broadcast it out to multiple machines. And we can use HyperOpt or Optuna to do distributed training. So each worker is testing its own combination of hyperparameters in parallel. So it's something that if you're doing 1,000 iterations on a single machine, that could take hours. Or you could say, I'm going to use Spark. I'm going to spin up 20 nodes of workers, and those hours go down to minutes. So you can get answers much faster. And that's a real selling point for using a distributed system on a single node problem.
Got it. Thank you.
Mm-hmm. So the next part here, we're just, this is a helper function that's going to allow us to keep track of what the state of our model is. Because passive retraining doesn't guarantee you're always going to be replacing the current existing production version. And Mflo's registry will only actually make an update if we're releasing something that's a candidate for replacement. We want to have a really quick and dirty place to sort of query the state of our project. I use Delta for stuff like that, where passive retraining, if I'm doing that every couple of hours or every day or once a week in a system where I could have dozens or hundreds or thousands of models, I don't want to have to go through and try to figure out what the state is of passive retraining by looking at actual job execution and historical runs. So what I can do is the state of passive retraining for each individual run to a table, and then I can query that. And we'll see that at the bottom, what that looks like. So the other thing here, the next part with registry logging and model registration, this is interfacing with Mflo's model registry. And what we're going to be doing is generating data structures that will specify exactly what it is that we're going to be logging. And the core guts here for this class model registration, this is our logic for that passive retraining that I was talking about, where we're going to say what is currently running in production, what were its results when it trained last, and what's its performance been on the recent data. And then when I do my retraining on the new data that's come in, the new training set, how does that perform against the previous model? So we can actually take the old model predicted on the new holdout data, take the new model on the same holdout data, and just see which one performs better. And if we get a better metric with the new one, then we actually register that model to the Mflo model registry and say, you're good to go, you're now production, and we're going to archive the old version of the model. But if you don't beat the current production model, then just write an entry to that tracking table that says, hey, I gave it my best shot. I wasn't better than the current production, but at least I ran at this date and time. So you can have that history of saying, okay, I ran here. Here's what my best metric was for the actual distributed hyper parameter optimization, and I didn't update for some reason.
What is the metric? Is it customizable? Is it a single metric or multiple metrics that
you can only, for hyperparameter tuning, you can only optimize on a single metric. So it might be for a regression problem like this. I think the example in this is just RMSE. Say, hey, here's our optimization metric for decision logic for what to replace. Say we were doing a classification problem and you're concerned with true positive rate and your false positive rate. You want to have some sort of understanding of what that space is. So you can create that logic to say, I need to be at a threshold that's better than current production for this metric and this metric. And if I'm not, then don't replace current production. So you can get pretty customizable with that, with the model registry aspect. But when you're doing hyperparameter tuning, you generally just optimize for a single metric and hopefully choose the one that solves the problem the best.
So how would that look like in this example for this data? This is the index or something, or the forest, right? So
this would be like the amount of the woods that burned is what we're trying to predict. So in that holdout set, based on the features that we have coming in, it's like how big of a scale was this forest fire? And we get the actual value, our label, our target is number of acres burned based on all the parameters that we're collecting. So our ML metric that we're using to calculate is RMSE. And here that I have highlighted, what we're basically saying is, hey, the production metric that we have for what has been in production up until that point, we're comparing it with the best metric of the most recent run. And if we're lower in the new run, then we're going to actually return this new run's identification key so that we can register that as the next model.
Mm-hmm.
And that's what this method does. So this register best, if we actually have an improvement to the metric that we're measuring, then we're going to be updating that model version. And that's what this is. If we have a flag to say, yes, we're going to update this to a new version of prod, we're going to be basically registering that model. So we're declaring, we're instantiating this object, this register model object here with the path of the artifact, the model that we're actually have generated and stored off to the tracking server, a new title that we're going to be writing to it. And we're going to be updating that registered model to say, hey, here's our new name that we're going to be passing in, as this is a registration event that's set as a candidate for production release. And then we're going to be updating that version saying, hey, this is the new version of this model that's going to be in production. And then we're going to actually initiate that conversion from staged. So when we put something into the registration service, you can use human in the loop to say, hey, I have a candidate here for release, and a human has to go in and say, yes, I approve this. So it's kind of just like a PR that you can do for model artifacts. What I'm showing here with passive retraining is we're automating the human out of the loop with that, because we're saying, hey, we understand this problem. We understand what the metrics are. We just want to say, if as new data comes in, if we're better than what we were before, we don't need somebody to approve that. We can say, yes, just push the new version to production. And that final stage here, this transition model version stage, would say, take it from staging, put it into production. And then if something exists before that was currently in production, we want to move that from the production state to an archive state. And this allows us to have that history of the registration service. So any organizations that have a need for auditing, and there's a lot of them now, particularly in the EU with GDPR and stuff, some of these regulations will say, hey, we need to know what was running in production 6 months ago or a year ago. We need to know the actual model artifact ID between those date timestamps. So if somebody needs to say, hey, what was going on with not only our data, but the model that was consuming that data and making predictions, you have a one-stop shop to say, hey, I'm not throwing that artifact away, but I can see exactly when that transition stage happened and what was running at that time.
So in this case, you're actually archiving after moving to production, or this is an operation that happens later? So
it happens almost instantaneously right after.
Okay.
So like milliseconds later.
But it's not overwritten basically. So,
right. Yeah, everything is immutable in here. So when you push something either to the tracking server or to the registration service, it generates a new hash key. So nothing is going to get overwritten.
Got it.
And then the final thing that we're doing here is that registry logging. We're saying, hey, we want to know, we want to have that table updated for whatever we just did here. If it was better, we want to be able to say, hey, here's the new version of that artifact, and we're writing an entry to that Delta table with this information that we're passing in. But if nothing actually changed, we want to be able to say in that table, like, hey, we ran, like the job ran, the passive retraining attempted to work, but it didn't actually update. And we'll see that down below a little bit.
No change. Yeah.
Yep. And here's a little helper function that allows us to retrieve all of this, basically the current production model for this project. We can get it in effectively 3 lines of code, allows us to get that artifact registered as a Spark UDF, so that if we have data coming in that we need to do predictions on, this is all you have to do for actually using that for inferring data and inferring predictions. So Mflo really simplifies that production aspect. If this was a standalone, notebook or standalone code in an IDE, there would be a couple more things you would have to do to pass in, which would, these methods here, the get current production and generate artifact path. There's not a lot of code that you would have to write in order to interface with Mflo in order to, get this predictor artifact from the registry. So this is all we're doing here, is just saying, for this particular project, for the latest versions that we have, give me the current production one, just return that first state of that, because that's a collection. And then after that, we would just get the from that ID, generate the artifact path, which would say, where on object store is the actual model stored? Give me that through Mflo, register the UDF, and then you can take a Spark data frame that could have hundreds of thousands of rows or millions or billions and do a with column operation on that. So that would stream the Spark data frame RDD information on each worker to that model in a distributed setting. So inference can, even though it's a single node model that's been built as, just on a driver on a small data set, if you're predicting a lot of data, Spark's a great use case for that, and it fully integrates directly with standalone Python. So the other stuff here, this is just standard demo ML stuff, nothing super fancy here. We're just generating some trained test data for this data set. The model scoring, we're, as you asked before, can we do multiple metrics? I always recommend doing that in all of my projects. I never just calculate one metric. it's so cheap to calculate a bunch of metrics, I usually do a lot of them so that if I want to switch later on to something else that solves the problem better for optimization, I can do that and have a historical reference. So to show that without doing what I would actually do in production, I would have far more than just these three. But for here, I'm doing just calculating MSE, the Bayes information criterion, and RMSE. So I generate all three of those. I return it as a dictionary mapping for the metrics that I'm trying to calculate. And then logging, this is the other part of Mflo where we're going to be taking information associated with this model run, and we want to have it stored somewhere in the tracking server. So we're going to be, this is a little bit different than how people would normally do this, but I have to pass in the trial here because I'm actually automating my hyperparameter tuning with Optuna. So that trial object, it's just a partial function that's iterated on multiple times for each of the tests that it's going to generate on its own. So I'm just going to specify a search space. It'll select its next batch of candidates for the hyperparameters that it's going to test based on, priors that it's received through its training cycle. And so I'm going to be passing that in to this method of log Mflo. I'm going to be passing my data in because I need to actually, calculate my metrics based on whatever it's testing. The model itself that's generated as part of that trial, and the parameters that were generated by Optuna. So it's just all the hyperparameters that we wanted to search through. And what it's going to be doing, the key to utilizing Mflo is just this one line. So it's just a wrapper around any operation that we're doing where we're interfacing with Mflo. So we just say with Mflo.start run, we can pass in a name that makes it a little bit easier for us when we're in an actual company using Mflo. We could have, a dozen, 2 dozen, hundreds of different ML projects being worked on concurrently across an organization. On the same tracking server, we want to have something where it's just for humans to be able to read and find, like, oh yeah, there's my project. I can get all the data from that. So that's all that is. But we're going to just say log the parameters associated with this one iteration run. And then we're going to be logging the model itself that gets generated. So that's just the sklearn model that's generated from a fit. And we're going to be passing in the signature. And that was what I was talking about earlier, where I'm specifying what is the conditions of our features, which columns in a pandas data frame effectively are part of our feature vector. And we use inference to determine that by looking at the model itself. What are the input features being passed to it? So that when we want to use this as a REST API or even for batch inference, we want to make sure that we can pass in data to it that has at least those columns in it or those fields in it, but you can have more fields in it than you actually, the model would be consuming. So it allows you to kind of future-proof stuff to say, hey, this model is just looking at these, say, 17 features, even though the full data payload could have 1,000 features in it. But you don't want to have the data science team merge up with the front end, software development team and say, anytime you guys add a column, you have to let us know because we have to change our code. That's a nightmare to deal with. So providing the signature means that you don't have to be dependent on them. They just have to you just have to make sure that they don't ever drop a column, or else, of course, the model is going to break at that point.
One question is this: part actually starts your run because you're actually this is with Mflo start run, but at the same time it's actually login, or
this will just be the interface to Mflo to allow it to write data to the same individual experiment that's being run. So that wrapper, anything that's in that wrapper just gets a reference to a hash key that's generated in Mflo to say, this is this one experiment, this one single model. The execution is actually down below, but we just need that so that we can actually log to the tracking server these operations.
Did you
the
log
parameters, the metrics?
Got it. But you only log the parameters. The data is still like in some object storage or something like that, right? You pass in the data here, but that data is still in in maybe Amazon S3 or somewhere else, right?
Yes. Yep.
Okay.
Yeah. You never log your data to Mflo.
Yeah.
You can
Okay.
log information about your data. So if you say, if I have a date timestamp associated with every row in that training data set, and you say training for this particular epoch of when I kick this off, you can specify that in a filter statement on your training data set, provided that your training is immutable and you're not, retroactively going back and changing old data. That's one way to do auditing, to say, as of this date timestamp, everything from here less than or equal to this is the training data that was used for this particular run, and you can log that as a tag associated with the Mflo. I don't have an example here of doing a tag, but it's similar to a log param or log metric. It would just be set tag, and you can say, you can write anything. It's just a dictionary of data. You could say, here's the name of my Delta table, or here's the name of my location on object store, and here's a filter predicate condition that can allow me to recreate this experiment if need be. If an auditor says, I need to see exactly the data that was used to make this model, that would allow you to do that.
Got it.
This is pretty standard, just ML stuff. We're just doing a simple random forest regressor here. We have our hyperparameters that we're going to be tuning, and these keyword arguments here that we're passing in, this is what Optuna is actually generating for us. So what we do with Optuna is we set these parameters of like number of estimators and max depth and min sample split. We're using that trial object from Optuna to just suggest something in the range between 50 and 2000 split up by a modulus value of 10. So it might try 60, might try 1980 for stuff. The way Optuna and HyperOpt do with their initial search space is an actual random generated search of seed values. And then after that, it's actually looking at using Bayesian probabilities as part of that tree of parson estimators. It's saying, where is on my next iteration of things to test, what is the likelihood of getting good performance based on the trials that have happened before. But the only thing you have to do is just set your search space, like somewhere between these numbers, or if you have a selection criteria, such as suggest categorical, we have these two options, either square root or log squared for doing the feature selection. You just specify it like that. And you can do integer selection. You can select out of a distribution through a normal distribution or log uniform distribution. And that's kind of what we're doing here. And then we're doing the fit here. And what we were looking at before, that log ML flow, that's what this is calling. So we're passing in that particular trial, the splits that we did, that's the data. Passing the model that we just built, that fit model from our train test split, and the parameters that were actually generated from this selection. So every time this is actually kicked off, params is going to have a value that is selected from these ranges. It's just going to be a dictionary. Now, actually kicking this off and running this, we just have some config here of, this is just us setting this up so that we can run it based on saying, here's where the data is going to be, and here's where we're going to log things to. And then because we're dealing with PySpark, we have strong typing on our data set, which is actually a really good thing for ML in particular. So we're specifying what the nature of that data is that's coming in that we're going to be actually using to do processing. So with this configuration all set, we're going to be calling our data ingest. And that's retrieving data from the UCI machine learning repository. And we're writing it out to Delta with this register data. And then from there, we need to get our data set onto the driver of the cluster as a pandas data frame. And that's what this is, that one function that was declared at the top of this. So now fire data is just a pandas data frame in a VM. And now to actually run it, run the training. We're going to hit that random forest tuning class that we specified above, passing in that pandas data frame, which is just all of our data. We're specifying a couple things. Area is the label, so that's area of like acreage burned in the forest. We're going to have a stratification key in order to do intelligent sampling. I did a little bit of EDA on this data set, and I found that the stratification point to eliminate collinearity as much as possible between train and test split is the X coordinate. It's just a grid coordinate system in the national forest to ensure that we don't have excessive skew between train and test, just to build a little bit more robust model. And we're providing some of those concrete values that we had up here of like, how long do we want Optuna to train for? And for the simulation to show passive retraining, I'm intentionally making bad models for the first round so that I can show it getting replaced with better models. So we're just going to do 5 iterations, and the conditions are not going to be that great for our search space. But when we kick this off, we're going to see that Mflo is going to start because we're initiating the tracking server interface for us to write data to it. So the first thing that happens is saying, like, hey, we're creating a new experiment because one doesn't exist yet at this location. And this is just in the Databricks workspace. And then immediately after that, Optuna is going to start. And Optuna is tracking our hyperparameter search space. So the first one that it came up with was these hyperparameters. Number estimator 630, max depth 21, which is it's a pretty deep model. Min sample split 76. It's just going to select these, and then it's going to return what that RMSE value is from its validation. And the next one that's going to kick off, trial 1, is going to use these parameters, 1050, 378, and its result was 51. So it wasn't better than the first one. So it's going to say, hey, trial 0 is still the best at 51.41. And it'll continue doing that. You could see it didn't do better than that first random sample that it got. It got 82 and then 52 and then 87, and then it stopped. But during the process of all this, what it was doing was logging to Mflo. And this is our tracking server log for this particular experiment, and it shows what was actually happening during that execution. And you can see here's where the actual hyperparameters are that were selected, and here's the result of the metrics associated with that. So its RMSE was 48.76. The ones shown here are actually subsequent ones because I've already run this demo this morning. But the original 5 here, we can look at that in a second.
So the lower the number, the better, right? So
yeah, on RMSE. So this is the actual tracking server interface, the GUI for tracking. And this will show all of the things that we've tried. So that first initial version of what we were doing to test out how well did the first iteration go. We can see what all of these look like by highlighting them. And we can hit compare. And this will kind of show us what the run results are. So as you can see, there's no overriding ever because we get this random unique run ID from each execution that happens. We have a run name, which is, just a name that we specify. In real production systems, that run name will usually have something to do with the project that you're working on and what was the additional feature that you're creating or change to the model that you made. Gives you the start time of when it initiated, and then it'll actually log all of the hyperparameters that were attempted to test on that run. So this is what Optuna came up with. You can see all of these are all over the map. And as the iterations, the trial number starts growing, there is a change to where it's actually searching. And we can look at a contour plot. This would be RMSE is going to be the Z-axis. So darker color is bad, lighter color is good. And you can see as, if we said trial number, as trial numbers went up, we start converging in areas where the numbers are much lighter and searching happens. If we're looking at max leaf nodes, we can see it's trying to search more in an area that it has prior success at, but it is still searching at places where it looked like it didn't have enough search capability to determine, was this really bad because of this hyperparameter, or was it an interaction that occurred with another parameter? But this tracking UI allows you to generate a lot of different charts. You can really explore what the search space looks like for hyperparameters for your particular model. You can do parallel coordinates plots as well. These get kind of crazy when you look at them, particularly if you have a lot of hyperparameters, but you can kind of see where does the convergence happen for good, RMSE values based on different settings that are happening in each of the hyperparameters that were tested.
Is this part of Databricks or this is part of Mflo?
This is Mflo.
Okay,
We just host it for customers.
got it. And then here you're using the same data set, right? So potentially some other runs could include it. You're adjusting the hyperparameters, right? But in some cases you may have a larger data set or something, right? That comes in later or something.
Yep, and then that would be its own experiment.
Got it. Okay.
So within a single experiment, the only thing that you should be messing with is the hyperparameters that are being tested. You can do cross-validation with Mflo as well, where you're averaging basically a bunch of train test splits and saying, hey, this is my average RMSE, or my weighted average based on how many cross-validation splits that I'm doing to make sure that I don't have a skew problem that's generating a bad metric.
Right. So they, like in real world applications, like maybe you're measuring, I don't know, some number of you could do it potentially with some images, like, so say license plates. So you're looking at you from a camera or something like that, and basically, as you have more pictures from more cars, then maybe the model can learn better, right? And then maybe you want to compare the data, right?
Yes, definitely. And that's where we're going to get right after this in the next part, is that passive retraining, which is, okay, we have a baseline model. So once we run this first experiment, we're going to get something that's the best of whatever we had for the initial run. And we want to say, this is production release version 1.0 of the model. So by calling this model registration, we can register whatever the best results were from that initial run to say, hey, I'm trying to optimize on RMSE. I'm interested in sorting by ascending order because lower is always going to be the best for RMSE. And whatever that particular run was that had the best value, register it as the initial, production version. And the registration is going to look like this. So this is the registration UI. This is the same between open source Mflo and Databricks Mflo. The only big difference is that Databricks Mflo allows you to do this. So you can enable serving directly from Databricks, and this will support low level, sort of low rate REST API access. If you have something that's like, hey, I have no more than about 20 requests a second, and I don't have 1,000 concurrent requests that may come in at one time, this will work out pretty well. And it's just a Flask, a Python Flask server.
Yeah.
Yep. Although this is going to be upgraded in the next several months to use Kubernetes serving, where we'll be able to do, you name the scale, it'll do it. But that's not part of open source Mflo.
But the Flask server, that's part of open source, right? So like in you don't have this UI, but then there's somebody who just like run a script or something to make it serve the model, right?
Yeah, that's pretty trivial. You would just basically specify a Docker container that says, what is my sklearn model artifact and what is my interface for that? Put that, like wrap that in a Flask app, and then configure, like specify your Docker build file as that YAML config, and say, here's my runtime environment. Here's what I need to actually generate that. And we actually do almost all of that for you as part of Mflo. So if we look at an individual artifact that's generated, this would just be one of those runs, not necessarily the one that is production or the best one, but one of the runs, we can see the values that it had. We can see its metric. And when you go down into the artifacts, we can actually see that it kind of helps you work with it in if you want to do batch predictions. It actually gives you example code to do that from within Spark or within a Pandas data frame. So it'd be that you can just take this code directly from here, copy it, put it into a notebook, and that's your prediction for batch. However, that doesn't really work for REST APIs. So what we do is we give you some information about this particular model, like what is the actual metadata associated with it. And this is what the tracking server will return to you. You can query this directly from an API. But if you want to build an environment that will allow you to have Flask and maybe Sanic wrapped around it, or you want to create a Docker container that supports multiple different dependencies that your system needs in order to interface with external systems, we actually build the initial Conda YAML for you that will give you that, the dependencies that are needed to reproduce this in an environment. And then, of course, we're giving you the location for where the pickled artifact actually is. So that is the actual model artifact and where it's actually stored. But this can be copied, downloaded, modified, will allow you to get that REST service up and running in less than a day, let's say. It's pretty simple. There's also the ability to push to cloud service providers. So you can actually push to Azure ML with a couple of very simple API calls, or if you're on AWS, you can just push the SageMaker and have that hosted as a flavor of MLflow.
Got it.
Now, the other part of this is seeing what that tracking table that I was talking about before, that Delta table. And this, we have that register information in here. So this is external to MLflow, but it gives us, a snapshot of what is actually going on. So here's our model that we're doing, the production version increment. So this is just the first one. It was updated because it was written for the first time, and this is when training was completed. And we'll actually hit this table 2 more times to show what it looks like over time. Now, if we wanted to do another passive retraining run, if we say, okay, we've released it to production, we have a retraining schedule set via a cron task that's kicking this off, let's say once a week. We say on retraining, we're going to have a week's more data available for training and for holdout validation. So we want to be able to capture this changing over time to eliminate the effects of drift that may happen because of the real world being the real world. So this retraining just gets kicked off. It's calling the same, that class that we created above, random forest tuning. We're just taking our new version of the data, specifying the parameters that we need, except now we're going to go from 5 up to 50. And we're going to change our validation holdout set so that we can hopefully get a little bit better performance out of this particular run. And it does the same thing that it did before. It's going through and trying a bunch of different hyperparameters on this data that has slightly different characteristics from the original production run. And we find that, it's actually performing quite a bit better than what the previous best was, which up here was 51.417, not so great. And already on here, we're down to 14.2. And it's continuing to test, and eventually it optimizes at 11.722 as the best RMSE for the hyperparameters that it found. When we kick this off and we go back to the tracking server, that is the updated values here. Instead of initial prod, it's all of these that we're looking at, these 50 runs. So if we look at these comparison, the RMSE in a lot of these samples is way better than what we had on that initial, 5 tests that we did.
Mhm.
But for each of these, we're actually storing off the model in case we want to potentially look at that artifact at some point in the future. It's all safe stored for all time. So that pickled up model is written out to object store. They're really small, 173 kilobytes, but we want to make sure that we have historical tracking for that, not just the parameters, but the model itself. And what we see from that run, because we had a better RMSE, that passive retraining, what it did was this used to be in production state. The new one came in, got production. We archived the old one automatically. Now you can go through and manually change the state of these. If we click on one, if you need human in the loop and you don't want to use API automation for this, you can go through and change the state of this. So these stages, you can actually say, I want to request transition to none, to staging, to production. Or if you are the owner of it and you have admin rights to this particular model, you can just brute force transition it to different stages. You can write comments in here in the description, and you can set tags associated with it as well. So these can be done through the API, or manually somebody can just add key values so that other people on the team can understand, like, hey, this is what I'm trying to do here. I wanted, I added 4 new features to this and it improved this. Can I get approval for this to be released to production? And then somebody can come in who has authority and say, oh, I'm going to transit from, take it from staging to production and then retire the old one.
Time check, we have 3 minutes left.
And that's, pretty much it for passive retraining for this demo. It kind of showcases the 2 big parts of Mflo, as this shows here on the page. We have tracking. We did take a look at that. It's recording all of our results for experimentation and for our potential production releases. Projects, we've been using projects this entire time. So when we're in this environment, this is a project. So this tracking of everything, we created a project that actually lives within the workspace that will actually have all of this registered to it. On the open source Mflo, you would have to specify a project title to it and all of the code that you're wrapping up into it. But on Databricks, it's automated for you. But it makes sure that there's a linkage between this development environment, the tracking server, and any subsequent artifacts that are associated with it. So if we're in the registry, we want to know what project was this part of, we can just go to source run and we can see, okay, this is the tracking service entry. Well, my code, where's my code for this? And this is the snapshot of the environment that generated that particular model. So you can see we are looking at a revision from when that model actually ran. And the other part is the models, which we did cover. We're wrapping up the model. We're providing a Conda YAML environment package in order to get this to be reproducible on different systems. So if you want to deploy something on Kubernetes, you can do that. You wanted to do it on an Azure VM, an AWS VM. You want to throw it over to SageMaker, Azure ML. You want to run it on GCP. You want to run it on-prem. Go ahead. You want to run it on your laptop? Good luck, but you can do that. So it just gives you this nice cohesive platform that eliminates a lot of the stuff that people such as myself have been doing ML for over a decade. This stuff used to suck, like really, really badly. Managing like what is running in production, how do I make sure that I know if what I'm messing around with right now is not going to break production, or how did it perform differently to what I was doing 3 months ago? This just gives you that that management system to make everything much easier. So that's pretty much the
Awesome.
demo. I don't know if you had any other questions or anything.
Well, I had all the questions, so this Eric dropped off. Kevin, do you have any questions?
No, I don't have questions. I'm still trying to learn the project.
Okay. All right. Sounds good. I mean, this has been great. Yeah. So full overview of the project. So one last question. So that UI is it's not available on Mflo. That UI is only available on Databricks, right? The one that you were showing, right? Or
These
Mflo have
UIs?
something? Yeah. Mflo has something like this, or this is all Databricks?
No, this is the Mflo UI. We just host it on Databricks for you. So
Oh,
you don't
okay.
have to spin up a tracking server. You don't have to spin up the model registry. You don't have to deal with any of the infrastructure. We host it for you. But the UIs, all the GUIs and the API interfaces, it's the exact same between open source and Databricks. So you can take something that you build on your laptop using MLflow and put it directly into Databricks and it'll just run. And vice versa.
All right, cool. So yeah, I'll post this video online, and well, thank you. Looking forward to just getting engaged with the community, and I mean, we're at CNCF TAG-Runtime, so MLOps is one of our spaces, right? So anything that the CNCF Foundation can help out with the project. I know Mflo might be already part of another foundation, and they may have a lot of maintainers. But the CNCF is always looking to collaborate with open source projects. So.
Okay, yeah, I'll let the development team know and see what their thoughts are. I know there's a lot of other stuff on the pipeline that is not necessarily 100% MLflow, but we're thinking about some potential open source projects. But
yeah, one of the things that we do as a tag, we're a tag, so technical advisory group. So within the tag, we can spin up these working groups. So if it's like some sort of a feature or technology that needs to, a group of people wants to get together and tackle that problem, the foundation can facilitate that. So in the case of something with MLOps that would fall within the scope of the tag, and we will help with that. And so.
All right, cool. Yeah, I'll let the team know.
Yeah, that would be great. Okay, thank you.
All right.
And yeah, I hope you have a great day.
You too. All right, bye.